How about that? We look at something called confidence intervals for the mean, population standard deviation known. That's going to be the difference between this section and the next section. The next section is going to be the population standard deviation unknown, meaning in this section we'll be given the population standard deviation, either by word population or, don't forget they can use the symbol that we're supposed to know here. We're supposed to be able to recognize. Well, I want to try to, I'm using my other tablet kind of crashed on me there, so I'm using a different one. Maybe I can find the stylus for it later. I'll just kind of freehand it for now, but that little thing right there, the little O with a hook, that's your population standard deviation. So it can just give you that, that means population. Of course, then the next, that's your S is your sample standard deviation. So, all right. So they don't have to say it in words. They can just give you, the symbols. That little letters, the O with the hook is a Greek letter sigma, which you definitely don't have to know that it's Greek letter sigma. You just need to know that it means population standard deviation. Now we're getting into the branch of statistics called inferential statistics, meaning that we are trying to use data from a sample to try to predict what we think population is going to be. Anyway. And we're doing it for the mean. If we were going farther into it, which we don't have time for in this class, I wouldn't mind if they brought proportions back into this, but if we were doing this for percentages and proportions, it's sort of like how polls work. We just ended a voting season here, so this isn't going to be percentages here. That's what's going on with those pollings. That's inferential statistics. You're trying to predict what's happening based on samples. But we're not doing it for percentages. We're doing it for means. So now the most basic way you can try to do that is what's called a point estimate, which means, you can use a single value estimate for a population parameter. That's fine. And this thing about the most unbiased, don't worry about that. But you can use the sample mean to try to estimate the population mean, which is fine in some ways. But if you have a large enough sample, but then the problem with that is, you're trying to throw a dart right at something and hit it perfectly by using just a sample, point estimate. You could be like kind of on the low side, kind of on the high side. Let's say, for example, you were trying to estimate the average female height in the United States. Sure, you could take a sample, couple hundred females, and come out with an average, and maybe you'll be okay. A lot depends on how you collected your data. You don't want all tall or all short women. You want to kind of mix it up a little bit. But anyway, the better way to do it is what's called an interval estimate, meaning that we're going to try to come up with an estimation where it's an interval range of numbers, and therefore we have a better chance that will actually fit in the interval than it does by hitting it with a single number. So, okay, let's kind of take a look at just kind of roughly how this works. So let's say for this particular one, there's no story behind what this problem is, but whatever it was, the point estimate, the X bar, remember that's the sample mean, your X bar was 12.4, and we'll talk about how we construct these here shortly, but just for the time being. So let's say your interval had a left endpoint of 10.3, and a right endpoint 14.5. And it's going to be the same distance from the mean, which is always in the middle, to either side. It's the same distance. Same, was it 2.1, I think? Yeah, anyway. A couple of ways you can write this is, so if you see answers in either form, whether it's homework or a test, they're both correct ways to do it. Parentheses means that's written as an interval from 10.3 to 14.5. Now notice this has the mu here, because even though this is X bar, you're predicting mu, the population mean. So we're predicting the population mean will be in this interval 10.3 to 14.5. We don't have to predict the sample mean. We already know it's 12.4. And then the distance from this sample mean to either end, because like I said, it's going to be the exact same distance because it's symmetrical, is called a margin of error. Okay. In this case, it looks like it would be 2.1, I believe. You don't have to do that in your head or whatever. So let's come down here. The level of confidence C, which can be certainly expressed as a decimal, but it's most of the time it's percentages. It's the probability that the interval estimate contains the population parameter. Population parameter, which is mu. It's the probability that it's actually in there. I mean, yeah, you can guarantee that your answer is 100% correct, but it could be possible that the answer would be meaningless. In other words, suppose that I claim that the average female height is somewhere between 3 feet tall and 10 feet tall. I'm probably 100% chance that's correct. But that's not useful information if you think about it, is it? Well, whoop-de-doo, anybody could have thought of that, right? So, we're trying to make this a little more precise, but with that comes the possibility that, it's not right, so you're allowing for the possibility that it's not right because you don't want just a 100% chance but the answer be nonsense. Okay, anyway. So common, it's not to mean they're always like this. I just threw this in there, but 90%, 95%, 99%. Obviously, you'll be given that, in the problem. But if you become a future statistician one day, you might, choose your percentage. Now this graph over here to the right's not real important. But I'm just going to kind of explain what it means real quickly. But it's okay if it, But this says 90% chance that your confidence interval will actually contain the mean. That means on average, if you collected, out of every, let's say you collected 10 different samples, it doesn't mean exactly 9 of them will be right and 1 of them will be wrong. It just means in the long run, about 1 out of every 10 should be wrong. Should be out, not contain it. Now this one's exactly showing 9 out of 10, just to give you a feel here, and it mentions down here in the long run. But if you can see, let me zoom in this a little bit. So these are just the dots represent the sample mean because the dot's right in the middle. And this vertical bar says, okay, suppose somehow later on, somebody determined what the mu actually was, the population mean actually was. Well, you can see the data used for the confidence interval in this third one right here doesn't overlap that mean, does it? It missed it. So that's what we're saying about. So it doesn't mean exactly 1 out of every 10 times, but on average, it's going to miss it. You're going to be wrong 1 out of every 10 times. When I say wrong, that's not wrong in the sense you do anything wrong. It's an error in the process. Anytime you're using samples to approximate a population, there's sort of a built-in error in there. Meaning you can't guarantee. The only way you could be 100% right, like I said, is you come up with a stupid answer, or if you know what the population data was, if you knew all the data, then you would just calculate the mean itself, and that would be it. So anyway, let me zoom back out of that a little bit. So you don't have to worry too much about that. I like that little graph there. So basically, a confidence interval is constructed by taking your sample mean, subtracting your margin of error, and then taking your sample mean plus your margin of error. So it's always, intervals are always written lowest to highest. So it's lowest, when it's written like this, lowest to highest. I'm trying to remember, maybe we'll look in the homework. Maybe I've seen some where they ask it as upper value and lower value, but they write it horizontally, like upper value, lower value. They might put upper value first and then lower value if they write it that way. I guess that's okay, but if it's written as an interval, it needs to be lowest number to highest number. It doesn't make any sense otherwise. Now we're going to see how to get this margin of error using equations and stuff and calculator, of course, but all right, so now suppose for right now we were just given this confidence interval right here, 33.2 to 47.6. So we're not worried about what the percent is. It doesn't matter whether that's a 90, 95%. That's not important for what we're just trying to ask right here. This says, can we find the sample mean X bar and then the margin of error E? And guess what? We can. Isn't that tremendous? All right, so the sample mean is always going to be inside the margin of error. In other words, I'm sorry, it's going to be in the, I'm trying to fiddle with something on my computer here and I'm messing this up. Let me say this again. The sample mean is always going to be the midpoint of that interval. In other words, it's going to be the, you just add the two numbers and divide by 2. That'll tell you what's in the middle. Add them together, divide by 2. So that's what I did right there. Yeah, I was fiddling with that computer. I misspoke there. All right, so now the margin of error is the distance from that value, which will be 40.4 when you add them divided by 2. The margin of error, I showed both ways to get it, but you only have to do it once because it's going to be the same number. It's the distance from that number, that x bar, to either end, to either interval, the distance, positive distance. So if you subtract it the wrong way and you get a negative, just take the absolute value of it. So it is 7.2 if you subtract 40.4 to either one of them. Another way to do it is you can subtract the two numbers here and divide by 2. That also works. Because the distance across is essentially 2 times the margin of error. Where did I draw that right up here? Yeah, like it's E one way, E the other. So it's 2E. So that distance actually equals 2E. So you subtract them and divide by 2. That also works. Anyway, let's look at how we calculate this margin of error. Now I'm going to kind of show this, a little bit, using the formula and the chart a little bit, but obviously if you're using the calculator, you're going to see that you don't have to worry too much about what I'm doing with the chart and whatnot. So because there is a calculator process for this, but I need to show it because there's going to be some, viewers that might be using the more traditional method to do it. Alrighty, so we have a z alpha over 2 times your, because these are going to be population standard deviation given, divided by the square root of n. Let's talk about what this z alpha over 2 means. You don't have to worry about the alpha. I'll tell you what the alpha 2 is going to mean, but it's also just called the critical value for the confidence level. But I'm going to show you how it's just alpha over 2 is a common way to write it. Now let me show you, if you were doing this kind of a manual way using the chart, here's how you do it. Now confidence intervals are always measured as, they're a middle concept. Remember percentiles? Percentiles were always based on area to the left, all the way to the left. But that's not true for this. The area for 95% confidence level, that means your middle area, perfectly symmetrical, that's the key, 95% is all in the middle. Whereas, percentile would be at some point where it's 95% all the way to the left. Now, our normal, I'll sort of show you this way, but I kind of came up with a quicker way to do it right over here. This N1 plus, and I'll show you what that is here in a second. It's faster than what I've got here. But this just sort of explains, why it's what it is here. So if you basically have 90%, 95% in the middle, the alpha over 2 represents how much is left at each end. Alpha meaning that's the remaining percent. So if 95% is in the middle, that leaves 5% total that's represented total by both ends. So then you would divide that by 2. So this is 2.5%, which is 0.025 area right there, 0.025 area. Now to use the normal chart, remember the normal chart gives you the area all the way to the left, just like a percentile would. So we're basically converting 95% in the middle to a percentile. So we don't need the 0.025 on the right here. We just need to know what that 0.025 added to the 9.5 in the middle gives me a total area right here of 975. Right there. That's what we need. So if you would use the chart, if you're doing it that way. I'll show you how to do it using inverse norm also too over here. We'll do that for a different one, the next one maybe. Well, this one happened to hit exactly, but you go in there, we'd be looking for the closest one to 975, but that one happens to be there. So it's in the 1.9 row and the 0.06 column. So that means now, anytime that we're doing a 95% confidence interval, that Z is always going to be 1.96. That's going to be, that number will be this formula right up here. That would always be 1.96. And now, see, and I'll do an inverse norm for a new one, but the inverse norm got 1.96. Now, be careful how I put the parentheses in there. Notice what I did, and I'll do it for the next one. See how I got the 1 plus 0.95 wrapped in parentheses, then that's divided by 2? Yeah, because a lot of people have messed this up where they do it without the parentheses. And if you go, let me clear this out. 1 plus, so in other words, to convert this to the percentile, the correct percentile value, it needs to be done like this. So I've had people in the past, and why am I not getting this right? Why am I having trouble with this? Because they did that, and look what happened. Oops. No good. Parentheses. Now, let's say we wanted to find the critical value, the Z, for some 82% confidence interval. So if you're doing it the old school way, chart way, I got the chart thing already cut out here, so I didn't even bring up the normal chart. Well, we have a new chart to learn today, so I think maybe I will bring up the new chart in just a second. But I don't think we'll necessarily need the normal one. Well, unless we go back and do something else. You may have other questions that require it. So I take the 82%, of course, it's a decimal. So I take 1 plus 0.82 divided by 2, 91. So that means I've converted the 82% in the middle and added the 9 on the left to make all of that be 91, like so. All right. Now, so I go inside the chart. I find the closest to 91, which is 0.9099. It's in the 1-3 row, and then the 0.04 column, and there it is. So 1.34 would be your answer. Now let's put it in the calculator. Yeah, here's a little, this is that next chart we're going to be using. I'll probably just bring up the chart by itself, so I don't have to be flipping up and down a lot here. So let's do the inverse norm. Now, one thing you could do is, if you want to do the 1 plus 0.82 divided by 2 first to get the 0.91, if you'd rather do that, go right ahead instead of doing it this way. I'll do it this way. In other words, you can calculate that number first, but I'm just saying you don't have to. You can let the calculator do it all. Just be careful, with your parentheses. Now, because we're calculating Z's, remember Z is the standard normal distribution. So Z always means you got 0 and 1 right there. Now, if anybody using an 83, like I did in my notes there, you don't have to have the 0 and the 1 there. I mean, I could even back over that and delete. There's no point backing over it and deleting it. Just remember, if you're using the newer, fancier calculator here, you got to change it to 0 and 1 if it isn't already. But anyway, there's the 1.34. I might cut this out of here, just snip it and see what. I won't worry about it. Let's see. And so, so I just had, see, it looks like I did just over there. That's what I did. And I just put the 0.91 in there. But I could have, done the 1.82. Let me cancel this. And where was it? Oh, yeah, I'm going to come over here and. Yeah, rectangular snap. Okay. So it's up to you whether you want to get that 0.91 first or just, I don't know. I would just let the calculator do it. If it was me, as long as you're careful with your parentheses, you'll be fine. Oh, where can I fit that? I guess I could squeeze it up there at the top, I guess. That's the problem. I start adding stuff to my notes there. It's finding the room for it. Because down here, I was just copying that same thing I had up here, which I guess I could get rid of that maybe. Well, whatever. I'll move this up a little bit. Okay. And I don't know. Yeah, sure, it's tempting to switch this around a little bit here and put this over here and move this out of the way and put this over here. Then show the two calculations to the right of it. Oh, I always like tinkering with these notes. Oh, I didn't want that. Yeah, there we go. So now both show the 1.34. Very good. Now actually we're going to be using this thing more in the next section, but let me go ahead and bring it up now. Let's see if I should have that chart in there, hopefully. Yeah, I could trim some of this down. So that should be in your notes. Let me know if it's not. Yeah, because this is going to contain what we're doing now and what we're going to be doing later. But you're not going to need much of this for this section, but potentially in the next one. So this top row, and I'll explain more about that infinity later. We get the next section, but this contains your critical values for different, and here are your confidence levels as decimals up there. Remember 95 that we looked at earlier? There's the 1.96. So someone that was actually using the formula to do these, this would be real convenient because you'd have them as a reference right there when you needed them instead of having to figure them out. But if you're using the calculator, you probably don't need it so much. We'll be using it a little bit more in the next section, a lot more in the next section. So this is just the same table right here. All right, I won't worry about reading that part there. So here's the formula again. So that's your margin of error. Earlier we saw that it's x bar plus and minus e. Then we saw that e equaled this part right here. Let's see. Let's see. Okay, so there's. Well, they're talking about the upper tail probability of alpha over 2, which is correct, but I like we're using the lower half, the alpha over 2 at the lower end. Okay. So we're just going to look at some problems here. We'll look at it both, real quickly with the formula, but I know you two. We're up to 5 now, or whatever. So I was curious if if you're calculator users, I'll make sure to. I'm not getting rid of this in the notes, but I'll make sure I focus more on the calculator if I don't need to. If you're not worried about this too much, but it needs to be there, and I'll explain it real quick. But so 35 days in a year, so n is 35. The sample mean of this stock Hasbro was 2320. Population standard deviations 4.34. Find the 90% confidence interval, the 90 and 95%, and which one is wider? Wider meaning farther apart. So here's the pertinent information for the first part. We're doing the 90. 23.20, 4.34, and it's 35. And then here, the 90%, that comes from, if you're doing it this way, right here. I can't, my little hand, I got a little hand there touching it, but there it is. I can't highlight it or anything. 1.6, well, I guess I can highlight it in my notes, couldn't I? Yeah, that's right. Well, I hate to keep scrolling back up to this every time, you know. Right there. So you see, that's, so somebody, you know, doing it this way, that makes that real convenient to find that number. But you're not even, you don't have to even find that number to calculate if you're using a calculator. Although, you know, like the one I did earlier for the 82%, I mean, yeah, there could be a question on exam 3 that's just asking for the critical value. Then you got to do the correct inverse norm and all that stuff to come up with the critical value. What I'm saying is, though, when I show you how to do this in the calculator to get the confidence interval, you're not going to have to tell it that critical value. You're only going to have to tell it the appropriate percentage, and it will do it internally. But like I said, you still need to know how to get it, you know, for that, you know, question that will most likely be on exam 3, where I ask you to find some random value off that, you know, well, random critical value. But it's easy to get with the inverse norm. It's just basically following what I did for that 82% one. All right, so here's all the numbers plugged. There's the formula. Here are the numbers plugged in. And you get 21.99 to 24.41. So we're saying we feel there's a 90% chance that the average for the year for the stock price will be somewhere between 21.99 and 24.41. Now, ready for the calculator? Now, because this is the older one, so it might look a little different than the newer one. Let's give it a whirl here. But it'll work the same kind of way. Now, we are using stat. This first time we'll be using test. Stat, test. We'll be using 1 and 2 later. Right now, this is a Z interval. We will be using T interval, which is the next section, and then we'll be using number 1 and number 2 in the next chapter. That's the only ones we'll be using. So Z interval, interval for confidence interval. Because sometimes somebody will pick that Z test and I go, this doesn't look right to me. I don't think something's right here. Yeah, that'd be the reason. It's because if it's confidence interval, you want the thing to say interval here. So enter. This one might look a little fancy. You want stats? I'll talk about what data does later. Well, data means if you just had like a list of numbers in there. That doesn't apply too much to this section because most of the ones with the population standard deviation known have larger values for n. So we're not going to ask you to do that for a large list of numbers, but maybe for a small list of numbers in the next chapter, which that isn't hard to do, especially in the calculator, when all you got to do is just enter the numbers into a list. But we don't want some, you know, obscene 500 numbers or something. What is this one? 4.34. I better double check these. See, there's a little O with a hook for standard deviation. 20, I already forgot. 2320. 2320. And it's 35. Confidence level, 0.90. It'll just get rid of the 0 whenever I move the cursor, but so you really don't have to put the 0 there if you don't want to. So you write it as a decimal. That means 90%. And like I said, it's going to figure out that critical value for you internally. And round to 2 decimal places is exactly what we got the other way. 21.99 to 24.41. Wasn't that exciting? I knew it would be. Now, for 95%, the only difference is that this critical value is going to be different, which doesn't concern you in the calculator, but if you're using that formula, it does. So you see the 95% is, there's 0.95 on the top. Here's the 95% number. It's 1.96. So all we're doing is changing the 1.645 to 1.96. If you're doing it that way, but I'm not, I mean, everything's written out here. I'm not going to just recalculate it. I also showed it in the calculator if you were just using keystrokes to do it with, you know, just punching the numbers in, but there's no need for me to show you that. Now, let's see, the calculator then is going to, we would just, all we got to do, we can go stat test 7, I get the number 7 is the interval, and everything's still there. All we have to do is change the confidence level to 0.95. Ta-da! So it's 21.76 to 24.64. Let's see. And there's, yeah, there it is. So now which interval is wider? That means the width. All you have to do is measure the distance between the numbers. But actually, I'm going to tell you in a second that I could have already answered that question of which one is wider without seeing any numbers, and you'll be able to perform that same analysis here in a second. But there's how, you know, measuring it. So you see the subtracting 2.88 is the wider of the two, 95%. And then when we talk about this question right here, it's going to come. But anyway, if you increase the confidence level, that means the interval is going to be wider. So the fact that between 90 and 95, the one that was the larger percentage would have the wider interval. And if you think about it, that kind of makes sense, because if you have a higher percentage of being right, it's going to contain more numbers in there. In other words, it's going to be, you know, if it's a bit bigger, wider range, there's a better percentage that your mean will fall in that interval. So that's kind of the theory behind it. Anyway. Now, since the factors affecting the width, E is the width, the sample mean has nothing to do with this part right here, because keep in mind the sample mean is just a fixed number that just sits there right in the middle, doesn't move, the X bar. It's the margin of error that stretches out the confidence interval, you know, because you're subtracting E and then you're adding E, so that affects how wide it is. So whatever affects the width is what affects E is what affects the width, nothing to do with the sample mean. Now, obviously, you have to have the sample mean to calculate a confidence interval, but you don't need it to answer these questions. Now, I'm going to assume that we cannot just randomly change the standard deviation, but the factors you could actually potentially affect yourself would be the confidence level. So you might, you know, as a future statistician, you know, you might decide you want to use a certain percentage. You can do that. And you change the percentage, and potentially you could change the sample size. So say you're collecting data, and maybe, you know, you collect 60, sample size of 60, and you have the, you know, ability, you can get more data. And so suppose you want to raise that to 100 or something, you know, like that. So you want to change it from 60 to collect a sample size of 100. So, but let's see how that would affect the width of the interval. Now, just how these working together means increase works together, decrease works together. So increasing the confidence level will increase the width of the interval. Decreasing the confidence level will decrease the width of the interval. So there we go. It works together that way. But sample size works the opposite. And you see that even though it's the square root of n, you see that's in the denominator of that fraction. It's in the bottom. And anytime that you increase the denominator of a fraction, the fraction gets smaller. That makes sense? Probably does. Hopefully it does. All right. So if you increase the sample size, you decrease the width of the interval. And if you decrease the sample size, you increase the width of the interval. So as a statistician, because obviously, that's called, when you decrease the width of the interval, it's called, make more precise, or that's the precision factor or whatever, you're making it higher, greater level of precision if you narrow it down, if you can narrow it down some. So let's say that you're determined to have a 95% confidence level, that's what you want, and you're thinking, I sure would like this width of this interval to get a little more narrower, more precision there or whatever. The way you could do that then is to increase the sample size. That's how you would affect it. All right, so you could see some word type question on a test, possibly exam 3 with that. So let's go back and look at some problems here. All right, fifth random sample of 52 NFL players at an average weight of 252.5 pounds. Assume the population standard deviation for the weight of all players in the league is 31.1 pounds. Determine the 80% confidence interval for this sample. So I just wrote down the pertinent information. And then, like I said, I'll show you where I got it if you're doing it this way. The 1.82 is right. There's 80% right there. And there's the 1.82 right there. So if anyone's doing it that way, just want to show you where I got it from. If you're straight up using a calculator, you don't have to worry about that. So I set up the formula. 252.5 plus or minus 1.82 times 31.1 divided by square root of 52. And got this interval right here. So there it is. You can see with just normal calculator keystrokes right there. But let me do the Z interval and see what happens. Actually, I'll just skip this one since you see everything. And obviously, you're going to see this done, homework here shortly. But I figure at least this one you can see everything that was entered. So I think I can probably get away without typing that one back in. Then so you see over what it gives the screen on the right. That kind of matches up what I got using the formula. So that's always a good feeling. How about that? Pretty exciting? I knew it would be. And let's see, same thing here. 30 students selected from a large group of students taking a certain calculus test. The mean score for the sample was 93. That must have been a pretty easy calculus test. Or they just happened to accidentally sample more of the better scores, which is possible. And standard deviations, so you see this time they use the sigma symbol instead of saying population, but same thing. Construct a 99% confidence interval for the mean score of all students taking the test. I guess I mentioned a couple of ways earlier how you can write confidence intervals. I guess this is a third acceptable way where they put the word to in there between them. Oh, that's okay. That's fine. That's okay too. That's all right. No trick there. Nobody's trying to trick you or anything. And just so if it's expressed that way, don't worry about it. And so for 99%, we got right here, there's 99. If you do it this way, 2.576. Obviously, many of you aren't going to care about that. And where was that? Oh, there we go. And wait, not that one, this one. So there it is, 93 plus and minus 2 point. Even though it's written plus and minus, like I mentioned, that's usually the way it's written, plus on top, minus. It still means, though, in an interval, it's written as the smaller number first. So in reality, you see over here in the calculator box there, I did minus first and plus second. We got 87.26 to, well, 98.74. I guess I just chose 2 decimal places. It doesn't, I don't know why I did, but obviously in my math lab we choose whatever it tells us to choose, right? Let's see. Okay, here's I won't redo this one unless somebody asks me later or something. So you see there was a standard deviation 12.2, the mean was 93, n was 30, confidence level 0.99, hit calculate. Yeah, I think that matches up pretty good with my answer there, doesn't it? This one with that one. When I say my answer, I meant using the calculation there. All right. Well, this one I sort of left blank here. Like I said, I don't have my stylus for this one. I can, if you're using the, well, okay, at least I've got the, the commands using the formula over there to the right. So even though I'm not going to worry about writing back over this, but I'll put it in the calculator though. I'll do that. So the 1.645, that's your critical number for 90%. I'm not going to scroll back up. So the mean lifetime of the bulb was 472. There's 77 of them. Population standard deviation 38. Pretty straightforward. 472 minus 1.645 times 38 divided by square root of 77. And then plus, I get these two numbers. So let's do it in the calculator. Remember, n was 77. I already forgot. 38, 472, and 90. $38, 472. %. All right, let's see if that's what I had there. I guess I could have left. Let me go back. Oh, I went second stat instead of stat. Okay, everything should still be in there. Yeah. I think I'll snip this one out and put it in the notes. Then put the one with the answer. I never can figure out where it's going to put these things sometimes. Okay, here we go. And now let me hit enter. Or calculate. I don't know why it bothers to show you the sample mean and then again at the below the confidence interval. I don't know. It doesn't hurt anything, but maybe there's some reason that I'm missing there or whatever. Okay. That matches up pretty well, doesn't it? Looks pretty good. Now, this is kind of an interesting conceptual question here because, understanding, without being too technically complicated, but let me just kind of clarify what I mentioned earlier, so in other words, what you're doing when you're creating a confidence interval, you are taking sample data and you are trying to predict with a certain degree of probability, which that degree of probability is the confidence level, you're trying to predict the probability that the actual population mean falls in that interval that you're creating here. So this, what does this say? A sample of 250 students. I didn't actually calculate. I got this from somewhere else in another old problem. I mean, I guess those numbers are right. I didn't check, but they gave the interval. I guess it's not supposed to be a trick. Hope the interval's not wrong, but I trusted them on this one. But 250 students has a mean of 14.2 credit hours per quarter with standard deviation of 2.5 credit hours. The 99% confidence interval for the mean is 13.73 to 14.607. Interpret the interval. In other words, the meaning. Let's look at answer A. 99% of the students take between 13.973 and 14. Okay, that's completely wrong. I mean, it's possible it could work out to be right, but that's not what it's telling you. See, the number of credit hours you're taking is going to be a whole number anyway. So either if it's in that interval, only 14 counts, but that's not what this is saying. You're not looking at a proportion of students that are taking it in that interval, so that's wrong. Now let's look at, so now skip ahead, same reason why D is wrong. D is sort of similar to A. The probability the student takes that many hours per quarter is 0.99. Once again though, the hours taken by any student is going to be a whole number hour. It doesn't need to be put in the interval. It's the mean that calculates out to, can be calculated out as a decimal number. So what this is saying here is, now let's look at, we got to be careful because B, and I mentioned I put a blurb down here. B is close to being right, but not quite right. We are 99% confident that the average number of credit hours per quarter of the sample students falls in the interval 30, whatever, blah, blah, blah. Okay. That's not right because actually we're 100% certain that the sample mean, because you notice where it says the sample, average, it says average here, and then, let's see, yeah, and then it says sampled down here. So, sampled, and then there's average number right there. Well, we already know it's not the sample students because we already know what that's one reason why I say it's 100%, because we know that the average of the sample students is 14.2. That's how you construct the confidence interval. So the key word there is sampled. Now, what you're assuming here when you read this problem is, and it's fair, if it was anything, it was supposed to be something different and make it clear. But when you say 250 students at a university, you're supposed to be doing this then for represent all students at the university. So that's what makes answer C correct. We're 99% confident that the average number of credit hours per quarter for all students at the university falls in that particular interval. So we're using the data from that 250 to predict what it is for all students. We don't know what it is. I mean, I guess obviously if someone has access to the computer system can probably, come up with what the right number is. I'm just talking about if you were just a regular person trying to figure this out that didn't have access to that technical information. So that's the difference between B and C. Because, we know what the sample mean is. So there's we're not, like say for B, we're 100% confident the sample mean's in there because the sample mean's always in the middle. Okay, so I think that's it for this section. So I'll leave that there if you want to look at that. So that takes care of this. Now, one thing, and was it last Wednesday I did? No, last Wednesday was a review. So I don't know if this was 2 Wednesdays ago or a week ago Monday where this came up. But anyway, but I'm going to address something now in the homework. There's something, I'm going to show you this right now. There's something in 7.2, one of those ones where like it's a part D or something or another. I really don't like that. If you do it the way we learned in 7.2, it's actually more complicated, but it's actually a confidence interval is what it's really doing, so it's better if we just calculate it as a confidence interval. You wouldn't have seen, but when you're looking at 7 and 2 before today's lecture, you would have had no way to know that. So I was actually showing a couple people how to do this. I don't remember if it was a Monday class or Wednesday class. I was showing a couple people how to do it. And I was saying, granted, you don't know what this means yet, but you know what this command does. But if they wanted to get the question right, now. All right. So, actually, I have 8.1 opened up, but not 8.2. Okay, I'll get that. I'll do that later this evening. I'm sure if you were really fired up to go, I'm sure 8.1 would be enough fun for you. I think you'd be okay without 8.2 today. But let me show you the ones I'm talking about here. And I'll just kind of check the answers, I'll show the completed problems. It's on either one or two of them here in the homework. I mean, I could show you how to do it without doing it as a confidence interval. Here's one of them. Let me just see if there's another one. Might just be that one. Might be, yeah. So that's only one. But it's so much easier for you to do it as a confidence interval. It was this third one part, the last part. But I could show it this way. The probability that 65% of the sample mean will be between what two values symmetrically distributed about the population mean? Well, that's essentially what a confidence interval is. When it says 65% in the middle, we're effectively calculating a confidence interval. So you can use a confidence interval for that particular problem, and let's try it out. I'm just going to leave these numbers there, and we already see, so that way I don't have to do a new problem, and I don't have to go back to the other parts. And at the end of class, if you want to ask me stuff from this, but obviously I don't want to do that until I'm through with everything else. But I want to show you this now because it ties in what we're doing now. So 65% being in the middle, let me see if I can finger sketch something here. It's not too bad. Now I'll get overconfident here and I'll mess it up. Yeah, so that's what this means. This means this is, better use my, whatever, I'll just use a different color. And that's 65% in the middle like that. So that's essentially just doing a confidence interval. So let me look at the where'd the preview go? Oh, it's down here. Okay. All right. So look at the very top of the deal. It says mean 2.59, standard deviation 0.03. So let me come over here. We're going to do a confidence interval. This will be a Z interval, even though we are going to use, because that's those problems we're pretty much giving population standard deviation. So stat test Z interval. Standard deviation is 0.03. 2.59. We are sampling 11. And we know it's 65%. So rounded to 2 decimal places, that's 2.58 and 2.60. I do believe that's what it shows in part D there, doesn't it? 2.58 to 2.60. You know, if you maybe later on want to see it the other way, I could show you. It involves doing 2 separate inverse norms. If you're dying to see that, ask me later, but I thought this would be just an easier way to knock that problem out. Because you're not, you're going to have confidence intervals on the test, but there's no way I'm going to ask a question worded like this as first part D. That would fall under the confidence interval category. So it would just be asked then as a confidence interval. No tricky stuff like that. Oh, you know what? Actually, okay. I won't actually work it out, but let me just do this real quick so I can move on. I'll go ahead and tell you. So 65% in the middle leaves 35% total divided by 2. So 17.5. You would have to do 2 inverse norms, where one of them to get the well, it depends on which one to get the lower number, inverse norm. The lower number means it'll be right here with 17.5%, so it'll be 0.175. And the upper will be those two added together. $65 plus 17.5, so that'd be 82.5. But like I said, it might have been tricky to figure out those two numbers. Now I'm trying to use a mouse. Obviously, I didn't put the mean and standard. I just started it off, the area. So, yeah, so these two add together, 82.5, that'll represent the right number. 82.5 will be the right one, then 17.5 will be that one right there. So yeah, that's how the problem was designed to work for that section. But I looked at it and I go, well, this could also be done just using a confidence interval, and that's something we're learning anyway. It's not like I pulled some magical thing out that we weren't going to be studying. It's just we hadn't studied it at that time yet. So, all right. So let's go back. Let's get rid of that then. That took care of that. That's good. Now I'll go to the actual section of interest here today, which of course is 8.1. Okay. Here's one where it's using the notation. I told you about one of the different ways you can write it, where the mu is between the two. Yeah, that's one way. And that was too basic. I say basic. I like for it to be. Here's an explain the meaning of the statement question, like we talked about that earlier with that one I included. Researcher selects 100 users of social media, over 100 million registered users. Analyzing the sample, she states she has 95% confidence the mean site spent per day is between 15 and 57. Explain the meaning of this statement. All right. Let's see. You got to be careful. Some of the wording can be tricky on this. Actually, let me read. I don't like A, but B and C both actually sound pretty good. Let me distinguish what's wrong with it. And even A has some merit to it. Let's see which one of these is the best one of these. Oh, B is no good. What am I saying? It's not B. It's not A either. It's got to be C. One is 95%. Oh yeah, because now I read it a little more carefully. The true mean time, the average time. We're 95. Not how much one person spends. It's got to be C because you're saying we're 95% confident that the average will fall somewhere in that interval. Okay. So let's see how we did there. Tremendous. Okay. I'll leave that one alone. Some of these. All right, let's get to that one's okay. This one's okay. These two, take a look at this and we'll go on break here shortly. The water one's okay. I'll do number 7. Light bulbs. Ooh, 4 parts remaining. We might just do this one and go on break, I think, because I keep forgetting about these things in the multi-parts. It can take some time. I'm not going to just necessarily cheat to look up these answers. I just want to see what the questions are because I'm going to undo it. Okay, it's got a couple of word things. Okay, this kind of covers a lot of it. Ooh, a lot of tricky. Okay. All right, this kind of wraps up all the conceptual stuff too. There's really only one calculation here, and the rest of it seems to be conceptual stuff. So, oh, fun, right? We get to think right through it, don't we? All right. Mean life, large shipment of bulbs, standard deviations 25. A random sample of 36 bulbs include a sample mean life of 270. Let's construct a 99% confidence interval estimate for the true mean light bulbs in a shipment. So I'm just going to do this via calculator. Just, you can let me know if, talk about it later, we can do it without. I can show you the other way to do it if you need to see it. And of course, I don't remember all the numbers here. Standard 75, 36, 270. I forgot which is which. Standard deviation 75. It's either 270 or 272. 270. 36. I think it's 99. All right, let's see what it wants. How about 1 decimal place? Thank goodness, it's all 237.8. And 302.2. How about give me a fantastic one time? Well done, I'll take it. Now we haven't talked about this idea yet, really. So this is good to answer this. this is more of a homework thing than really something that I would put on a test. But to kind of claim, to make a claim, and we're going to talk more about this kind of stuff with hypothesis testing later on, but the next unit. And if they're gonna claim a certain amount, it needs to fall in the value needs to fall in the confidence interval. So if you're trying to claim 320 and you're saying there's a 99% chance it's between 237.8 and 302.2, I don't think you can accurately claim that there's going to be 320s. And I mean, it's not impossible, but nah, I don't think they have the right. It says worded. Does not have the right. A mean of 320 hours is, standard errors. We have to actually calculate that. So let's come over. Standard error is a standard deviation divided by the square root of n. So let's see. N is 36. Standard deviation 75. Which is really just 6 here, but 12.5. Now I'm going to kind of do this in my head a little bit, but just if you go 12.5 plus 12.5, and you can use a calculator obviously, but 12.5 plus 12.5 is 25. So if you add 25 to this 302.2, you'd get 327.2. So 320 is definitely within that. So that's the reason, because it's not that complicated of a choice here, so that's why I just kind of did it that way or whatever. So I'm within 2 standard errors below, above the sample mean. So it is highly unlikely that the sample bulbs are, let me think this through right here. Let's see. Less than 2 standard errors above, yeah. Oh, wait, above the sample mean. No, I'm sorry. I picked the upper limit right here. Excuse me. Let's go back. Sample mean is 270. So 270. Oh, 270 to 320 is 50. Yeah, and look what, let's see, and look what this number times 4 is. All right, I would have got it wrong. 12 points times 4 is 50. So 4 was the answer here. Above the mean. I was looking at above that upper limit for some reason, but we're talking about above the mean, so I was measuring it the wrong way. But still, I agree with the highly unlikely. So let's see how we did here. Ooh, okay, I'm glad I caught that. Must you assume that the population light bulb is normally distributed? All right. Remember something that we actually covered in 7.2, and maybe you hadn't looked at it yet, but that's what that central limit theorem was, especially in this case since we know the population standard deviation. And then and the sample size is large. 30 was the magic number, in other words. It's more than 30 with the population standard deviation. The central limit theorem says you can assume that the sample mean is going to be normally distributed, even if your original data for X is not. So I think we're looking at D here. So in other words, you don't have to assume that it was normally, the light bulbs themselves don't have to be normally distributed, but those averages we calculate are going to be normally distributed. So that's what it's saying here. Fantastic. Oh, there's another numerical calculation. Change the standard deviation to 60. We can do that pretty quick in the calculator, right? All we got to do is go second stat. And two. Let's see what decimals. Does it still want 1 or does it want 2? Wants 1. I'm going to go 244.2. And the upper is going to be 295.76. Oh, I got it. 0.8. I can't even follow my own instructions there. Well, not my instructions, their instructions. I just copied it right off there. They wanted 1 decimal place. So come on. Excellent. Well done. I'll take it. All right, here we go, the standard error thing again. Now, the standard error is going to be different because the mean is different. I mean, the standard deviation is different. So it's 60, and sample size was still 36. So it'll be 10 this time instead of 12.5. All right, the manufacturer 320s, no, definitely does not have the right. A mean is, so from 270 to 320 is 50, but now when it was 12.5, it was 4 above because 4 times 12.5 is 50. Now hopefully this one will have 5 as an answer choice because now that 10, it's 5 times 10. There we go. 5 standard deviations. I'm sorry, 5 standard errors above the mean. So it is highly unlikely. Nice work. Yay for us. I think now is a good time for a break. What do you think? I definitely need one. So I got 6:45. I don't know. Is 10 minutes enough or you tell me? 6:55, or if you'd rather wait all the way till 7, we can do that. What do you think? Oh, somebody popped up in the chat. Well, go. Let's see what kind of exciting chat action we have here. Come here. Oh, one. Try it again. Come here, chat. Somebody said 7. All right, that's fine with me. Now it's 6:46 anyway, so my computer clock says 6:46. So let's rejoin the show at 7 o'clock here. So, all righty. See you in a little bit. All righty, welcome back to the show. Where did I put my, oh, here it is. All righty. So let's see what kind of fun we can have now with the next portion. Get rid of this, and I guess I could have had that next one up there for you. Sorry about that, but righty. The T distribution. Also known as students' T distribution. This fellow named Gossett, he published under the name student. Let's see if I can find why, I don't know. Seems kind of odd. But he, let's see, so let's go back to this. I'll come back to this in a minute, but sometimes there's a problem with estimating these estimates whenever you don't know the population standard deviation, and and especially if the sample sizes are smaller, and I'll talk about what I mean. Technically, if we don't have the population standard deviation, we only have the sample one, we use this method. But I'll talk more how it relates to the last chapter. But with smaller samples, that's especially true. Now, what I find amusing about this is this guy was working as a statistician for Guinness Brewing Company. So he's probably, sat around, maybe had a few beverages during the day and came up with this. I don't know. Hey everybody, look what I discovered. No, I'm just kidding. But yeah, he he's using statistics way back then. So chief brewer, look at him. Okay, all right, but I think it's funny he was kind of using a brewer, so I joke about whether he'd had too many beers when he came up with this. Anyway. Now let's talk about what this t distribution is. It's very similar to the z, the regular normal distribution. It's bell-shaped. It's symmetric. But here, though, it has the sample size actually affects the shape of it. There's not just one t distribution. It's a family of t distributions, as it says right here. And they differ from based on the sample size n. So that's what's going to make the difference here. Now, so it's showing and I'll talk about what the degrees of freedom means here in just a minute. It's actually n-1. But anyway, so this is like, these are different shapes based on the sample size. I know we learned way back in the normal distribution that how it got skinnier and wider because of, whether it's a small or large standard deviation. That's not the case here. It's based on the sample size. So these are different ones. Now it has this infinity over here. It doesn't have to really be infinity, but the idea is that as n gets larger and larger and larger, the t and the regular normal z kind of become the same thing. They're pretty close. Some authors, and I'll talk about this down here a little bit, they use the 30 or more rule, which that 30 seems a little low to me. That if it's 30 or more, you can use the z no matter whether you have sigma or you have s. And I've taught it that way before because that's what a particular book has done. But in reality, if you have sigma, you're supposed to use z, and then if you have, no matter what the sample size is, and if you have s, you're supposed to use the t. But the idea is if n was 200, for example, that's a lot better than 30. If n was 200, the answers for the confidence interval would be really, really close. If whether you use t or z. But you have to be careful in your world here because smaller, these will be smaller values for n, so you'll have to know when to use and t and when to use z, but it's all based on the standard deviation, which we'll talk about that as we go here. Okay. The degrees of freedom, I know is df equals n-1, is the value that we use when we're finding the critical value for t interval process. I'll show you the calculator. I usually like to use the chart for this, but you can use the calculator if you want to. I think the chart's pretty convenient. So for example, if n equals 20, degrees of freedom would equal 19. If n was 13, degrees of freedom would be 12. That's going to be very important. I got a whole big blurb down here at the end. Read it, not read it. It's not on the test here. It talks about the idea behind degrees of freedom without getting too mathematical. Because it actually can get quite a mathematical. Like say, for example, let's say you have three numbers, x plus y plus z equals 15. That 2 is confusing. I don't like the way they did that. It looks like 15 times 2, but you see 2 is actually 1 and 2 are references or whatever, not I don't like that. I would have put it out to the left somewhere or something else, you know, got it out of the way. But let's just say x plus y plus z equals 15. And they're saying, I usually do this in a face-to-face class, and I'll let people pick the numbers. But this one is, they chose 8 for x and 2 for y. That's fine. So if we choose 8 for x and we choose 2 for y, we've chosen 2 variables. We can't choose z, because if x plus y plus z equals 15, that means z would have to be 5, right? Because then 8 plus 2 plus 5 would equal 15. So the idea is that the degrees of freedom of choice, there were 3 variables, but you were free to choose 2 of them. So that's sort of the idea. But once again, all you got to remember is n minus 1. And here's another thing over here where they, you know, let's say if you knew the sample mean, and then you could choose, let's say there were 5 variables, and if it told you the first 4 numbers, this was 3, 4, 5, 6, and the mean was 5, there were 5 variables. The mean is actually 5. There's also five choices, 5 numbers. You can't, the last one would have to be 7 to make it average out to be 5. So you had n minus 1 scores were free to vary. They could be variable. Then the last one had to be the particular number to make it fit. So, okay, this is not super important, but every once in a while somebody, I don't know, degrees of freedom, what? In your world, all you need is n minus 1. Now, so you see, here's where that infinity comes back in. I put this, some books, I like doing it better this way, because some books, maybe even this book, they put the infinity down at the bottom, but I like having it right there on the top row, just because that way the z's are right there on top instead of looking at a bottom of a chart. So this is the idea, kind of like we're talking about infinity. Well, whatever, you know, it doesn't have to be literally infinity, but it means this chart is t distribution. It's based on t, but if that degrees of freedom is super, super large, those numbers in the top row are essentially just the z values anyway. But now, so here's how you would read this chart: is you'd find your confidence level across the top. And actually the next chapter we'll be using the 1-tail, 2-tail stuff. But you decide the confidence level on the top. And then you have to find what row it's on. See, for the z, everything was in that top row. But here it's based on the df, the degrees of freedom, the n minus 1. I just copied 1 page. Now in the homework, you may have problems where it's larger numbers there. On the exam, I always, for these kind of problems, always keep them under 30, and you only have to use that 1 page. But in the homework, that may not be true. We may have to bring up the, you know, more of the distribution, which we can. So I don't know if you're the kind of person, if you print stuff out to be prepared for the exam, or you just kind of reference it on a different computer or open up a different web browser. I don't know, whatever you do. Yeah, but if you print this for testing purposes, I promise you will only need 1 page. But homework, hey, I wouldn't print it out just for homework. I'd look it up. So you do the row meets the column. And here's the whole business about explaining with a book. So I was saying earlier about the idea of 30, but and I'm mentioning I'll keep them at 30 or less, but really in theory, 30 is, I don't know, it's not all that good, but well, let me show you. Here it is at 29. You see, let me just pick any of these. I'll pick the 1.96 for the that's for 95% right there, 1.96. And then for 30, the critical value is 2.0452. You can see these numbers are decreasing. That's the idea. They're decreasing, and they're working their way towards 1.96. They're not decreasing all the way down to 0 or whatever. That's why 2930 is, I don't know. I don't like it. But, you know, a couple of hundred would certainly be probably okay. We're going to try that in the calculator, actually, and see. So I'm going to use the table. I'm going to show the table for this, and I'll show this little calculator. And you can try it in there if you want to. One thing about these versus the Z, you know, the last section I did the one, find the critical value. I did some random percentage, like 82% or something like that. Even though the calculator can do that, I I'm not going to do that because at least without the calculator, you could still do it with the reverse table lookup. I showed how to do that way. You can't do that here. The math is too sophisticated. The calculator people could do it, but the non-calculator people could not. So I'm only going to, for our problems, I'm only going to use critical values that are on that chart. I mean, you can still use the calculator, but I'm not penalizing someone for not having the calculator, in other words. So everything's just going to be, that's no big deal to you, but I was just not, that's what I mentioned that. So let's say if it was 98%, so I'm trying to find so there was Z alpha over 2 before, now it's T alpha over 2. That makes sense. N is 98%, confidence level is 98%, N is 13. We have to subtract 1 from this for our degrees of freedom. Very important. So if it's N is 13, degrees of freedom is 12. So I'm going to go over here to 98%. I'll highlight that. Of course, I'll try to make this, it's going to be too big, but I'll try to make it where the 12 is in the center of my bar. There we go. Yeah, covers most of it. There it is. You see that's on the, I kind of dipped down a little bit, didn't I? But the 12 right there to the left, I'll do that. There we go. 12 degrees of freedom. There's your critical value, 2.6810. So it's not that hard to use this table. Like I said, even if you have a calculator, you might feel like you want to use it. Or not, whatever makes you happy. That won't go away. Okay. Go back up. 80% for N equals 24. So 80%, N is 24. That means degrees of freedom would be 23. All righty. So here's 80%. That's the second one. Degrees of freedom 23. How about right there? 1.3195. Let's see how we do. Is that what I have written down here? Okay. There we go. Now in the calculator, we still have to kind of convert it to a percentile like we did before. So you still have to do that thing I showed you in the last section where you have to go 1 plus the confidence level divided by 2. So you see how I got that all in the parentheses. You got to do it that way for this. Here's another thing too. Yeah, that's why this one I use it. I think this is only in the 84s and the newer 84s. I don't think the 83 has this function. So you can't even do it if you're in the 83. That's why we got to focus on the chart also. Because if you got an 83, you're going to be using the chart. Because I don't think the 84, I don't think this inverse T is in the 83 list. Let me think where it is here. It's going to be, I forgot where it was. All right, calculators. Oh, here we go. It's frozen. Okay. Is it second distribution? Yeah. Yeah, I don't think the 83 has this. But if you've got the 84 and you want to use it, but don't worry about it. Yeah, here's the, so I'll do 1.98. Or I can just do 1.98 because 1 plus, right? 1 plus 0.98 is just 1.98. And then here it's asking for degrees of freedom. I wasn't sure if it would ask for degrees of freedom or N, because it could have converted it. Obviously if it would ask for N, it could have converted it to degrees of freedom. Well, that's what it wants here in the old 84s also is the degrees of freedom. This was 12 degrees of freedom. Yeah. So once you get to this part, it looks exactly like what I already have in the box there or whatever. So, so 2.68 for that one. So, yeah, I knew there was that reason. It was, let me actually, no, that's not what I wanted. I'll go ahead and just snip this out just so people can see it's in the distribution menu right there below the inverse norm. We'll fit that in there somewhere. Yikes. All right. I will be doing other ones later. Probably I won't worry about calculating that next one right now. And I'll figure out where I want this. Actually, I can do this. Well, like I said, it's not that hard to use that chart, so it's not the end of the world if you have a 83. It's not going to be the, oh no. The good news is you're still going to be able to do T intervals. You're going to be able to do those with an 83. It's just this particular feature is not available. All right, there we go. So you're okay. Now, the confidence interval setup is pretty much exactly the same. Its structure's the same, but notice I'll circle this. The only difference is instead of T alpha over 2, Z alpha over 2, it says T alpha over 2, and the numerator, because we don't know the population standard deviation, just has S instead of sigma. But the format, the structure, the calculation is pretty much all the same. So that's good news. And then I'm going to show you how to do it in the calculator with either kind of calculator. In a random sample of 7 computers, the mean repair cost was $100 and the standard deviation was $42.50. Assume the variable is normally distributed. That's important here. I hopefully don't have any problems that don't say it, but in theory, that's important because that was one of the conditions for the T distribution. Because remember, if it's the more than 30, like that question we had in the last section, the central limit theorem kicks in. I'll get to the chat question here in a second. But because, you know, it's a small, it's got to tell you that it's normally distributed to be able to use the T distribution. So now it says it wants the margin of error, and then we can construct the confidence interval, so it wants it separately. So let me see what's going on in here. You can't calculate it. That's the point. You have to use the chart if you want just that number. You'll see me do an entire confidence interval here and using it just a minute. I'm saying you cannot get that. If it's a question just asking for that value, you cannot get it in the 83. That's what I'm saying. Cannot be done. You have to use that chart. But like I said, the good news is you will be able to do the confidence interval, though. You'll see that. That will work for the 83. I don't know. It's just a feature they did not have. They just added it in the 84. I don't know what to tell you other than that. All of a sudden they decided to put that in there. But the point is, it's so easy to look it up on the chart. That's not really that much trouble. I know some people that I've had classes before with 84. They just look it up on the chart. They don't even want to mess with it. But not assuming if that was just the only question it was asking. If it's asking for the confidence interval, then they don't have to worry about anything. But I think the chart's easy enough. So n equals 7. It's going to be a T distribution because, how do I know that's? First of all, if it's population standard deviation, it's either going to say the word population or it's going to have the little sigma symbol there. But because this is the continuation of the same sentence, it's part of a sample, so that would also imply that that's the sample standard deviation, because that's the standard deviation from those 7 computers. All right. Now, all right. Now, of course, I'll show you how to get this. The margin of error, if you were doing it manually, here's how you would do it. The margin of error is always the part that's after the plus and minus. Now, let me show you. I'm not even going to do the inverse norm on this one. I'm just going to show you where the 2.4469 comes from. You can try it in the calculator and see if you get it. But so it's 95 and a 7, so that makes it 6 degrees of freedom. %, 6 degrees of freedom right there. 24469. That's your critical number. So if you do it in the calculator, you should get that same number. So the margin of error technically is 2.4469 times the standard deviation, which is 4250, divided by the square root of 7. Now let me make something clear here, because usually this is a question people will ask, especially if I have, it's a lot of people in there. So I always try to catch it before they ask. The subtracting 1 for the degrees of freedom is only necessary for looking up that value on the chart. In this formula right here, n is n. You use the actual value for n, which is 7. So no, you don't subtract 1 there, you use 7. I get 39.31. So you take 100 plus and minus that number. The smaller one goes first. So you subtract, you get 60.69, and then you add, you get 139.31. Now, everybody can play now with this. As everybody can play, that means TI-83, you're in the game here. And let me show you how you can get this. You can do it without this formula right here. You can just get the confidence interval. You can get the margin of error that way too. So it's pretty straightforward for either calculator. So we go back to stat. Well, fairly straightforward now that we've seen the Z. Just be careful you pick the right one here, because that's where people mess this up sometimes on test. It's a T. I went too far. It's a T interval. And the mean was 100, I think. I know N is, I think it's 4250 for this. And a 7. Confidence level was, I don't know, 95. Ta-da, this gets you the confidence interval, just like, just like that, just like I did it right there. So this is pretty similar with either calculator. Let me show you how I can get the margin of error. If you do the confidence interval and it's only asking for the margin of error. Let me go back to my scratch page here. Oh, that was the wrong scratch page. None of that matters, but that was somebody asking questions on Monday night, preparing for the test. Oh, let's see. No, I didn't do anything here. Okay, let me come. But this is where it comes into the idea of a margin of error. I'm going to try to do this freehand here. So, it's your X bar is in the middle, and the distance it goes that way is E, and the distance it goes this way is E. So to get each end of the interval. So if you subtract the higher number minus the lower number, and you see, so the distance all the way across, E plus E is pretty much 2E, isn't it? That makes sense? E plus E is 2E. So all you got to do is take the width, the high minus the low. So let's say that you went ahead and did the confidence interval in the calculator because that was easy. And now I just go 139.31 minus 60.69. Keep that in parentheses. Or I could have done that, hit enter, and then divided by 2, but I'm going to do it all in one step. Yeah, because that represents 2 times the margin of error, that whole width. Because you're going, so that's why you have to divide by 2 here. And there's that 39.31. Or you can do it the other way I mentioned earlier. That's one way to do it. Another way is, once again, you do the confidence interval, and you don't have to even do, it might be easier just to do it the way I'm about to tell you. It's just, remember the mean's always in the middle, so you can just take the upper number minus the mean, and that will give you the margin of error. That's probably easier, actually. You don't have to do it that other way. So in other words, 139.31 minus 100, 39.31. So you didn't have to use this formula to get it. Well, let me take that back. I don't know, I don't do this on a test, but I don't know what's going to happen in the homework, because if they do one of these in the homework and they don't give you the sample mean, We probably, actually, you could probably just make up a sample mean and it would still work. We may have to use this formula. I think it might work even if you just made up a sample mean. Let me see something here. Let me take this one and I'm kind of curious now. I'm going to change n to 200. Leave everything else alone. Yeah, that would work. Now that's obviously, so if you weren't, if it was only asking for margin of error and it did not give you the sample mean, you can just make one up and then you still see, you take that upper number, 239.31 minus 200, you would get the margin of error. So it wouldn't matter what the mean was. The mean is only critical is if we need to know what the confidence interval is, then that's totally dependent upon the mean. But for the margin of error, we would not even need the mean. We could do it without it. If it didn't give it, that would not be a problem. So, all right. Oh, one thing I want to show you here. Let's see. Go back to that. I know the 83 people don't have this, but the inverse t. I was telling you earlier how t will turn in. Let me change this to, I'll do for 95. Oh. So that would, and then I'm going to change the degrees of freedom to 200. So that means n was 201 basically. So I want to see how close this is to the z value. Yeah, see, let me go back over here. And see the z value for 1.96, the z critical value is 1.96. And then you see that calculator thing gave you 1.97. So that's the point I was trying to make earlier, is that, as n gets larger and larger and larger, you're getting closer to what the z is, in other words. So, but 30 is not big enough. But if someone, so almost for 300, 200, so obviously, even higher is even better. But it wasn't, what was it, 1.97? I kind of went away from that pretty quick. But yeah, when, it's for the z, it's 1.96. So, just real quick, quickly, I'll just change this. I'll do a second enter and make it 300. Oh. Then I'll quit messing around with this. Yes, it's getting closer and closer to 1 point. So that's what I was talking about, how as n gets larger, the t, even though it's a different graph for whatever n is, that's why it's a family of distributions. But then as n gets larger and larger, the t and the z merge into the same thing, basically. Okay. All right, so back to this. So so really the key on this is you just have to make the distinction, because it's very possible on an exam that some of the problems, I don't always intentionally do this, but I don't mind if it does work out that way when I pick problems, as it might have the answer there for both t and z. So if you did it the wrong way, you might have thought you got the right answer. So, oh, cool, I got that one right, and not necessarily. So we have to just pay careful attention, whether it's t or z, and then once you know that, you can just whip it right out in the calculator. So, and we got it. Okay, sample 17 shoppers, average 5380, sample standard deviation. There's your, there's I actually put the word sample in there. So, and then along with this sentence right here, assume the grocery, well, obviously we'd still have to do it as a t, even if that wasn't there, because we have no other options, but just for correctness there, it kind of needs to be there. Assume the grocery bills are normally distributed. Determine 80% confidence level for the population mean. So the first thing we have to figure out, is it a t or is it a z? It's a t, because it's the sample standard deviation is given, it's telling you it's normally distributed. So N is 17. So even like I said, if you use 83, you're not going to be doing it this way, but I'll show you in the chart real quick. N is 17, but it's 16 degrees of freedom. %, I believe, is the second column there. Yeah, 1.3368. And then there it is if you're using the formula. So that was the only number we had to get that wasn't already given in the problem. So it's 53.80 the mean, plus and minus the critical value I just got off the chart, 1.3368 times 18.40 divided by the square root of 17. All right, let's see. And so there, I just showed it if you're just using a regular calculator. Let's do the t-interval process here. Stat, test, t-interval, number 8. All right, so I don't know what all these numbers are. Let's see. 5380 is the mean. I think it's 1840. 17 is N. Yeah, it's kind of interesting because on that, using that inverse norm thing, inverse T thing to get that critical value, notice that it asks for the degrees of freedom, but here it wants N. So, and it will take it internally and convert it to degrees of freedom. So if you're even bothering to use that inverse T for anything, just be careful. It was 80%? Yeah, 80%. Oh. Oh, how's that look? Well, I already have that answer. So 47,835, that's already in the note. So yeah, over there to the left. Okay. But at least you got to see the input of it there. Well, like I said, it's a smidge off here on the low end. But not, I want to say off. It's not because of anything wrong. Technically, that would round to 47.84. I can tell you why that happens. Yeah, I mean, you don't have to care, but it's not important. But it's because, you know, when you're using the method of the formula, we know we're using 4 decimal places for the t. So what can make it slightly be different is when the calculator's doing it, it's doing a process mathematically where it's calculating that t and it's calculating it to more decimal places. So this number has more decimal places when it's internal in the calculator. You don't see there, whatever. Well, actually, if you do the inverse, well, I tell you what, we can do the inverse t on that one. You would see it, wouldn't we? Yeah, let's just show you. Let me show you that. I keep forgetting to hit second. Yeah. So that's 1 plus 0.80 divided by 2. And degrees of freedom. Let's see. 16. Yeah, 16 degrees of freedom. 1/6. So you see that the difference. Yeah, it's using that number when it's calculating the confidence interval instead of rounded to 4 decimal places. But not a problem. Should not cause you any grief or anything. Well, I just wanted to put that out. We've seen that happen before anyway. And we've also seen the homework's been pretty good about that as far as, well, like we were doing some of the normal distribution stuff. If you were using normal CDF or if you were using the chart, it looks like the homework was set up to accept both those answers, which makes me happy because I hate for it to be only one way or the other. And then all you had to do on the test was just pick the closest one. You know, it was the test answers were based on the chart, but you could still use normal CDF, just pick the closest one. So, all right, so there we go. Knocks that one out. We having fun here? Look at that. All right, we're testing some chicken eggs. How much more of this we got? Let's see. Oh, the last page was that. Oh, this was, no. Yeah, that was the degrees of freedom. Is there something after that? No, okay. That would be the last one. We don't need that anymore. Oh, it looks like because I was editing this earlier. Oh, I got a big back gap in here. I probably should move these notes around a little bit, shouldn't I? I'll do it later. I won't waste time now. But I think I can condense that other problem to put it on this page. So, oh, not that one, chicken eggs. Oh, we got a lot of them, chicken eggs. Come here, chicken eggs. We can go a little faster now we got the hang of this. We're testing chicken eggs for cholesterol. 193 milligrams was the mean cholesterol. With S equal, okay, so just telling you S, that's sample standard deviation. And here's the bit right here above it where it says assume the population has a normal distribution. Sometimes it'll be up in here instead of actually in the, well, on a test question, it wouldn't be that way. It would be contained in the problem. But you might see it this way, like on a review problem or something like that, where it has that information right there above it in the description. So 95% confident, okay. So we want to be, based on this estimate, we're trying to be 95% confident that the mean cholesterol for all chicken eggs, all such eggs, where would that lie? So obviously, if you have a 95% chance you're right, that means you have a 5% chance that you're wrong. But what's okay? That's fine. All right, so let's see what we got going on here. Could be good. And I did it here with the formula. I'll kind of skip past the formula a little bit if you're not going to be using it. But it's there, obviously, so people can see it. And I figure if you are using it, you can just come by and ask me if there's something that doesn't make any sense there. Well, let's look at the T interval. So yeah, just let me know if there's something in the actual formula, but if you're just using the T interval, you don't really care about the formula. You don't have to care. And let's see, 193, was it? I'll double check that, obviously. I want to say it was 12. Oh, 12. 193 was right, but 15.4 is the standard deviation. I don't know why I thought it was 12. Oh, 12 is what N is. That's where I got 12 from. All right, I didn't remember the confidence level. Yeah, I circled that 12 there because sometimes people fuss at me. They don't like it whenever a number is written as a word. They'll be looking for everything. It doesn't stand out as much, does it? I've had people tell me like face-to-face class, especially when they sit right in front of me. I don't like it when a number is written as a word. You'll be all right, though, in case it comes up again. So there's your 12. It was 95%. Okay. So I'm getting 183.22 to 202.78. I don't know if the one for the Z answers there or not, but it is for this next one. So we're going to take a look at this one. Like I said, it may have the answer there if you use the Z, but that's not correct. So that's, I don't do that on purpose, but like I said, I know it happens. This next one's a good example. Alrighty, coffee soup machine at the local bus station. Supposed to fill cups with 6 ounces of soup. Bus station vending machine soup. I don't know about that. I might take my chances on the coffee, but I don't know. The soup might be a bit of a gamble. Yeah, here's another one where there's a word instead of a number. 10 cups are brought, mean a 5.93. Standard deviation is 0.13. Construct a 99% confidence interval for the true amount. And then here we go with the assume the population is normally distributed. So that's what that, you know, and we say we don't have a population standard deviation. So we're definitely dealing with a T here. So there's the key numbers, and here's you get the chart number there. So degrees of freedom will be 9 because n is 10, 99%, and 9 is right here. Let's see. Right. 99 and 9 right there. 3, 2, 4, 9, 8. So I just wanted to show that again in case anybody was kind of showing that less and less now, but okie doke. I guess I used 3.250. I know I used to use a chart. We used to use a chart that only had 3 decimals instead of 4. So maybe that's what I didn't just round it on purpose. I wouldn't round it, use whatever number's there. I probably should be using 3.2498. I might change that later so it doesn't confuse people. But I'm betting when I changed it here, I forgot to change it there. But anyway. So we'll do the T interval. Yeah, one confusing thing is that's part about fill cups with 6 ounces of soup, meaning that you don't really use that 6 in there. But notice this answer, and then goes back to that question we had in the last section. Would that be sufficient enough for, could the whoever's in charge of the bus station vending machines, can they make a safe claim that it really is pouring 6 ounces of soup? And I would say, yes, I would agree with that this time because the 6 fits in that interval. Unlike that other problem, remember we did with the 320 or whatever, it was outside the interval. This one's in the interval, so I would go ahead and say yes if that was being asked here. But anyway, all right, so 5.93.13. .93 .13. N was 10, I believe. I think it was 99. Should probably double check that, but it feels good. 593 13 99 10. Woohoo! Got it right. How does that look? Yep. Looks like right here, and it looks like right here. Now here's okay. Now I didn't put all the input in there, but I'm just showing you if you would have done this on this one as a Z interval. Let me zoom in. I'm not going to type it in there as a Z. You could yourself if you want to, but you did it as a Z interval. This particular one, I'm not saying this is always going to happen, but look at those numbers. If you mistakenly did this as a Z, you would get answer choice D, 5824 to 6036. And you'd feel pretty excited there. Okay, I got it in there and there's the answer. No. So you made the mistake of choosing Z instead of T as a distribution. So I don't know, that could happen, may not happen, but like I said, it may not be every question, but so that's why you just have to be, as long as you're careful between your choice of T and Z, I don't think these will be that difficult. What do we got here? 27 Exxon customers, 16.1 gallons to fill it up, 5.4 sample standard deviation. Assume the number of gallons is normally distributed, so we have a T distribution. Determine the 99% confidence interval for the mean. All right. Heck, I think I'll just skip over to some of these just so we can get to the homework. But anyway, if that's okay with you. So there it is, using the formula, the number off the chart, and then I didn't show what I entered, but it shows, the my answer matches it. But it does show you what I put in for the X bar, the SX, and the N. And then obviously I would have put in 0.99 for the confidence level. And you can see it's clearly highlighted that it was a T interval there. So, yeah, I figure I'll move on just so we can get to some homework. All right, this one. I'll do this one in the calculator, though, since you don't see anything else there. But I won't mark it down or anything. I won't save it. But 13 hotels and rooms in Boston, average rate of 172.10 with a sample standard deviation of 2390. Assume the room rates are normally distributed. All right, there's that along with a sample standard deviation. That's our, I mean, obviously that sentence could be there for the Z distributions also. It just doesn't need to be there. Well, as long as if it ends other than 30, it'll be there. But this is your real key, not so much that statement only has to be there is if you have a sample standard deviation. But there's the real thing that makes it the T. And I'm also going to use mostly under 30 here, rule 2. So, all right, so let's put this in the calculator. At test number 8, T interval, 172.1. All right, 2390. I think it's 13, but I'll double check when I go back and get the confidence level. I'll make sure that's 13. 13. Oh, it's 99. 99's already in there. Let's see if it matches what I indicated is the right answer there, 151.85. It's 192.35. Love it. Okay. Knock out a couple more of these real quick. I'm going to just skip this one. Nothing wrong with it. It's a perfectly good problem, but I want to get to the one after that. That one, because that's a completely sort of different thing there, or whatever. So I'll scroll down past that one. Yeah, it's some of these. I don't mind leaving those examples there, but time's always got to be a factor, and then especially with wanting to look at least one homework problem, that's always good. Now, we're not doing it. I'm just doing this in the calculator. I'm not even going to show it this other way here. Of course, you could use Excel to get the mean and standard deviation for this if you wanted to. Remember, we had that stdvedev.s for sample or something like that. But anyway, use the TI 80, whatever, 384. You can do this much easier to do it that way. But I'm just saying somebody can get. So what I did here is that this actually is just giving us loose numbers here now. It's not giving you the mean and standard deviation, which means that needs to be calculated. The sample mean, it's telling you the sample data, and then sample standard deviation has to be calculated. So we know that n is 5 because there's 5 numbers, 90% confidence interval for the mean. So that's what I'm doing here. I'm calculating the mean. I'm calculating the sample standard deviation. 90%, 4 degrees of freedom because there's 5 numbers here. So n minus 1 makes it 4. Got that off the chart. Plug it right into, all right, wait a minute. Oh, there it is. Okay, sorry. I was looking at the wrong number. There's the 2.132 from the T, and then here's your standard deviation, and then divided by the square root of 5. That gets you the answer. It's perfectly correct. It's a bit of a nuisance, but the calculator is a thing of beauty. You have to put it in a list. It's 2, 3, 4, 7, 9. quit out of that. Now we're going to go to stat, test, t-interval. Now here's the difference, what we've been doing. Stats means, which is pretty much the way all is mostly going to be done, but this is the one exception, means you're given the mean and standard deviation. If we go over here to data, data means like what we just did. Data means your numbers are in a list and the calculator needs to calculate the mean and standard deviation. We won't be entering it. So you'll see it'll be a different looking input when I go over to this. I hit data. Look at what okay. Yeah. I'm in L1. That frequency just needs to be 1. I don't know why. It just needs to be 1. But see, you don't tell it the mean and standard deviation because the calculator is going to do it for you. And then that needs to be 1. Why? I don't know. I don't remember what the confidence level was, what I picked for that problem. I don't know. Let's see. 90%. Okay. And calculate. And round to 2 decimal places. And then right here, it's telling you then what the mean and standard deviation were, you know. Hey, by the way, here's what it was. So 2.22 to 7.78. And I think that's what I got working it out the long way. Yeah, 2.22 to 7.78. And here it is. Right. Yeah, there's the input right there. You can see it. And then same answer instead of doing it the long and grueling way. So that might come up in the, I haven't edited this section of notes yet, but I wouldn't mind leaving one in there if it's in there. Okay, it takes care of degrees of freedom. What is it, 754? Okay, so that gives us time to jump into the homework. Now, of course, I'll make sure that I pick a problem that I know I'm not going to delete, you know, because obviously that'd be a waste of time. But I need to go through here later and prune out the remainder of the homework. Well, our semester is pretty much flying along here. Yeah, you see I haven't set that up yet. We've only got 2 more weeks of lecture after today. Everything else will be, uh-oh, it logged me out, didn't it? Too much time? Boo. All right, I guess I'm going to have to get completely out of this and start over. Will it let me? Well, let me try one more time. I mean, should have 8.2 preview. Maybe that's it. Oh, somebody put something in the chat. I'll check here in a minute. It might have timed me out when I didn't realize it. So let's see if this works better. And I'll check what was going on in the chat. Somebody might be trying to help me here. If this doesn't work, then I'm gonna come over and see if you were helping me. I'll check you in just a second here and let's just see. Before I do any problems, I'll check what that chat question is here. Let's see. Hopefully that's all it was, just a little timeout kind of thing. All right, that's tremendous. So that's what it was. Let's see what's going on up here. It is not, that's correct. It's not posted. That's what I said that earlier, that one's not ready yet. I'll work on it this evening and get it ready. So yeah, you can't see it, but I mean, obviously from my point of view, I can see it and we can still kind of look at it at least anyway or whatever. So, right, I'll get that up soon, but you can at least see the problem, and the good news is you can go back once the video is posted. You can go back into this part in the video and just watch this part. You know it's going to be near the end. So yes, that's not ready, but it's still worth it for us to do it. I'll have this one posted probably later tonight or open up. That's what I was joking in the first half of class, and I'm sure that you know, you'll have enough fun if you want to do some homework tonight. At least anyway, you could do 8.1, but I'm not saying you want to, but then I can have this ready to go for whenever that's going on here. So, all right, let me, yeah, so you the students cannot see this, but you can see the screen though, right? I mean, you can see what I'm doing, you just can't access it yourself. Oh yeah, here's what I was talking about. Yeah, you see, so you'll have to use more pages of the chart, the T chart, that that I was showing. Usually these are larger numbers, but you can bring it up from here or use my chart. Let's see what there's. I think there's, if I remember correctly, it might be kind of confusing. Let's see. So the 1 minus alpha, that means that's what the confidence level is. Or I guess if you could do the calculator, if you felt like you wanted to do that, you could do it. But you're not if you're using the 83, you got to do this. I'm just looking at these big numbers. Yeah, this chart sucks compared to mine. I mean, as far as user efficiency, because you have to kind of think your way through this. So you see like part D here, like it says 1.99, n equals 55. See, mine, I have the confidence labels. I think mine, if you look at my entire chart, it does go that far. I mean, I was just using the snipped one in the notes. I mean, I made this up myself. I can make it go as large as I want, really, but I think there's about 4 pages. Yeah. See, this one's better. I'll show you because what percentage was that? 99%. So let me, which is the far right column. So it's 54 degrees. If n is 55, it's 54 degrees of freedom, 2.6700. But here's how you have to think through it using what they've got here. You've got to think of it, well, either by the cumulative or the upper tail. You got to think of it. So 99% leaves 1% left over. So you have to think through it like this. Half of 1% is 0.5%, which is 0.005. So you would have to realize that this 005 column is the same as saying 99%. And then there it is. There's the same numbers. It might be hard to see there. 2.6700. So mine is easier because you could just look up the confidence level directly. Here you have to think about how much area is in that upper part every time, which is I find a bit of a nuisance. But other than that, then that's how you can get all these critical values. But I'm going to kind of go put we can come back and look at that, but I just want to jump it. I'll probably keep that one. Let me look through these. I got to check. Let me look at all the parts also too, because like I say, I don't know what I'm going to eliminate just yet. You know, if I'm going to eliminate anything. 9 problems, something may have to go here. I didn't mind that having the individual numbers. We just talked about how to do that. So that looks pretty straightforward. We can do one of those kind of ones that has a little word follow-up to it. Yeah, here's one where you'd want to use the calculator for sure. 15 of them, kind of a pain, isn't it? I know how to get the mean, standard deviation, all that kind of stuff in Excel. I think there's, I'm not sure if there's a direct confidence interval calculation in Excel or not, like there is in the calculator. I don't know. By the time I'm not going to figure that out right now. I got too much time, but by the time we do all that, we can enter the numbers. I'm probably going to leave this one. This is 15 numbers, a little rude, but I wouldn't do this to you on a test. Don't see anything bad that needs to go. Oh, I don't know. The numbers look kind of stupid on this one, so this one might go. I don't like all that 0, 0, blah, blah, blah. That one may have to go. And This one looks okay. Let me go back to wait, let's see. Oh, heck no. Oh, no, 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 no. That's got to go. That's far too rude. We got to draw the line at entering 40 numbers, I think. What do you think? I mean, that's just rude. I don't like that. I mean, this one's pushing it in my book, but all right, let's do this one real quick. If that's okay, if you want to do this one, because that's the one we'll just type it right in there. And oh yeah, see, so that's why I got to go through. That's why I do that. I'm sorry I didn't have this one already ready. I got busy doing some other stuff, but that's why I do this. So I can usually every section I usually eliminate a couple of them that are just a disaster. But this one's less of a disaster, I think. Except my memory is no good. Oh God, I wish I could go over and get my phone off my desk there and off my nightstand and come and take a picture of this instead of toggling back and forth. That might be, sorry. Because I know that, yeah, I can't say, hey, shout those out to because you're looking at whatever screen I'm looking at, right? So we can't work as a team here, can we? Because even if you wanted to help me, you couldn't. Wait, clear, stat, edit. I'll just type right back over those. 73863. Oh, actually, here's what I've done before. Where's my pad? Let me get a piece of paper out. It's written them down. That's what I should be doing. I can write them down real quick and actually type them in faster, I think. There we go. That might be faster than trying to go back and forth. So I'm gonna get a scratch piece of paper here, and I always try to keep myself some stuff handy. All right, 738-634, 582-684. Wait, 654. Almost messed it up. 837. 950 713 676 591 492 653 553 90831 967. Yeah, I don't know if this is going to be any more efficient or not. We'll see. Of course, it's a lot faster if I can use my fingers and type them than this. Also, 634. I wish they had one of these. I'll look back. Maybe this one will go too, because I might look at that one that there was one of them that had two different calculations. They had like 8 or 9 numbers each. That one may go. Just keep this one. But I was trying to see just if there's one of them that was just a little less involved typing wise than this. I'm guessing that one with, one of my students one semester, I never have used it, but they were using that, whatever it says, stat crunch. I never looked at it. They looked into it. That might be with that one with, I'm not going to worry about it, but that one with the 40 numbers, that one might be designed to download and stat crunch, whatever that is. I don't know the commands well enough to do it, so I don't want to try to teach it just yet, or whatever. But I guarantee you, if it's going to be on exam 3, it's going to be something like that one I did with the 5 numbers or whatever. It's going to be something very timid, maybe 6 or 7. I don't know, but not some mess like this. But certainly not the one with the 40. And I probably would use integers. Oh, I just messed that one up. 9.67. All right, well, so there's 15 numbers there, and that shows 16, 15 numbers. So I'm gonna go second, quit, and now I'll go stat, test, t-interval, data again, okay. All right, I don't remember the confidence level in the question. 95. Oh, I forgot to take the answer off of this one. Sorry. Well, I'm not doing it now because I've already typed those numbers in. I meant to undo the check, yeah, and have new numbers, but we're not doing that now. We'll just make sure it matches that 95%, and then I can just explain those other ones that already have the answers there. So does it want 2 decimal places? Yeah, so 2 decimal places, 633 to 789. And there it is. You can see the answer. 633 to 7899. Interpret the interval constructed in A. Okay, one of these kind of questions. I like these. You know, one of these could slip on a test, maybe, you know, because I had it in the notes and it's here also. I don't know the weird about the conclude with part there. You know, they could have just said it could have just said we are 95% confident. Sometimes the way the wording's done is weird, but we are 95% confident that the population mean for the dollar spent in the restaurant is contained in the interval. Yeah, that's definitely the correct answer. Because they're saying they mean the entire fat. Once again, B is wrong because of the word sample right here. Yeah, we know the sample means in there for sure. It didn't use the word population, but here it was implying for all customers. I probably would have said something like that. Lunch for all customers of the fast food restaurant. I would have make this a little clearer on the exam, I think that it is here. What assumptions must you make about the distribution? Okay. The population is normally distributed, which you saw in those examples that I was doing. That's the assumption that goes with it. And do you think this is assumption's reasonable? I don't like this. Hopefully that'll be the same answer when you do this. So pay attention to this. If this problem even stays, I don't know what I'm going to do yet, but I don't like the appropriate plot business. I don't want you doing that. I don't want to mess with that. Hopefully that will be sort of the generic answer every time you do this. Let me release it. Then that's okay. Let me check it again and see what's got new numbers now. So yeah, that's a different confidence interval. Okay. That looks like that's going to be the standard answer for that part D. So if this one makes the cut, then just go with that. Then don't put too much effort into that. So 811. I don't know if did you want to see one more real quick or something? Or you want to do a quick one? Maybe one that doesn't have like 10 parts to it here. Yeah. Any of these? That's I guess I can watch here. This time I'm gonna. Yeah, this one we'll do it where we're just calculating it, you know, without typing all the numbers in. Oh, this one's fine. I'm thinking one I'm pretty sure that would stay. Yeah, any of these two would stay. Yeah, this one I don't know what I'm going to do with on that one yet. But so let me go forward to either the 16 or the 17, because both of these. All right. I think this one's fine. They were about the same type of problem. This will work. We'll call it a day. And of course, I can stick around for other stuff here, you know, but that'll at least officially cover these two sections right now. And then I'll get at least 8.2 edited and ready in the next hour, probably. Okay, actual wear of tire claims that graded 150 on the sidewall, graded 150 the sidewall tire. A random sample of n equals 17 indicates the tread wear index is 137.4 and sample standard deviation of 25.5. So there's your t interval. So assume that it's normally distributed. Construct a 95% confidence interval. Okay, this won't take long. And so we don't have to go through all that business again, thank goodness. We will go back to stats now. So now we go back over to stats because we're going to be telling it all the mean and standard. Yeah, so that's just it just keeps the information that was in there from that data list we had. No problem. That's why we type right back over stuff. The mean's 137.4. Standard deviation was 25.5. Uh, 17 was sample size. Oh, I forgot. I should have looked at that too while I was over there. Oh, it's 95%. Okay, so that just got okay. 95%. Let's calculate it. How many? 2 decimal places. That's good. 124.29. And the upper is 150.51. Let's see how we did. Excellent. Do you think its consumer organization should accuse the manufacturer of producing tires that do not meet the sidewall of the tire? Well, it's kind of close, but I would say that, you know, we should not accuse them that it doesn't meet. In other words, because the 150 is in the interval, just barely, you know, but I think, no, we're not going to confuse them of not being in there. In other words, kind of a double negative thing there, you know. So a lot of times these problems mean yes. Whenever it's in the interval, you say yes. But because it says that do not meet it, so we're saying no, we're not saying they do not meet it. Does that make sense? The wording's a little tricky, but I think it's this one. No, because the grade is actually in the interval. So we're not going to accuse them of lying, in other words. Or I don't hate to use the word lying, but of making a mistake or whatever the reason. So they might not have been wrong on purpose, in other words. It's only lying if you know you're wrong, misleading someone intentionally. You could do it accidentally. So that was right. So that solved that problem then. So, all right. That will officially end the lecture. I need to just step away for a real quick restroom break. I don't need the 15-minute break like we had between the two halves. So if you just give me a couple of minutes, I'll be right back. So, so any questions you may have? So I'll just start talking. You know, obviously, if you're not back when I'm back, that's okay. But I'll just start talking whenever I'm back, so you'll know. So I'm not going to give you a time because it's only going to be about 2 minutes. So I'll just start talking when I'm back. And if you're not sure, you can talk. You know, hey, are you there? So let's see. Where's the pause recording button? What's okay? I'm going to delete it. I've been doing that in the videos. I just delete everything that's asked.